This sample problem is related to collision in 2 dimensions. A hockey puck with a mass of 0.170 kilogram traveling along a straight line at 1.50 meters per second strikes a stationary puck with the same mass. So this is the hockey puck that is traveling in a straight line with 1.50 meters per second, and it strikes the stationary puck with the same mass. Stationary means at rest. The first puck exits the collision in a direction that is 30 degrees away from the line at a speed of 0.750 meters per second. So after the collision, this puck here moves with a velocity of, so the final velocity of puck 1, V1 final, is equal to 0.750 meter per second at an angle of 30 degrees. And we need to solve for the speed of the second puck after the collision. So we need to solve for the V2 final. So to solve this equation, we must just look into the momentum of this object before collision and the momentum of the object after collision in the x and the y axis. So let's start with the x-axis. Momentum initial in the x-axis should be equal to the momentum final on the x-axis. So before the collision, we will have m1 v1 initial on the x-axis plus m2 v2 initial on the x-axis is equal to m1 v1 final on the x-axis plus m2 v2 final on the x-axis. And now let us look into the final velocity of object or of the puck 1, the final velocity of the first puck, or V1 final. Now if you notice, this is actually our V1 final. So that's our V1. Let me label that. That's our V1 final. And this V1 final has the following components. We have the V1x, so this is our V1 final x. And we also have our V1y final. Now our V1fx is a side that is adjacent to the angle theta. So this is our theta right there, and therefore we could say that V1fx is just equal to V1f, or the final velocity of mass 1, multiplied by cosine of the angle theta. Correspondingly, the y component, or the vertical component of the final velocity of this object right here, would just be equal to V1 final sine multiplied by sine of the angle theta. Because once again, our V1y final is the opposite side with respect to the angle theta. Alright, so now having said that, let us expand our equation further. So once again, our V1fx is just equal to V1fx is just equal to V1f cosine theta. So let us substitute our values. We have m1, which is 0. The mass of the puck is just 0.170 multiplied by the initial velocity. So the initial velocity of this puck right here is 1.50 meters per second. So I will have 1.50 meters per second plus m2, which is 0.170. And since m2, which is this object right here, is actually stationary, so that means its initial velocity, whether it's on the x component or the y component, it's just equal to 0. It's not moving. Is equal to m1, which is 0.170, times V1F final, and again V1F final in the x-axis is just equal to VF cosine theta, V1F cosine theta rather. So our V1F is 0.750 cosine of the angle theta, which is 30 degrees. So this is our V1F on the x-axis plus our M2, which is 0.170 times V2 final on the x-axis. So now this is actually our equation, and you could just use your calculators to solve for the unknown, and in this case our unknown is the final velocity, or is the x component of the final velocity of the second ball, or of the second puck, or our V2 Fx, and that is equal to 0.85 meters per second. So now we have the x component of the final velocity of the second puck. Let us set that aside. We will go back to it later. So now we work on the final velocity, or final vertical velocity of the second puck. So we will start with the same process for the x component, but this time we will have y. So we have PIY is equal to the momentum final on the y-axis. So I would use this same expansion once again. I will have M1 V1 initial on the y-axis plus M2 V2 initial on the y-axis is equal to M1 V1 final on the y-axis plus M2 V2 final on the y-axis. And once again, my V1 final on the y-axis is equal to, we have it here, VF, or V1F sine theta. So I'm just going to substitute that there. I'm going to put it here. My V1 final on the y-axis is just V1 final on the y-axis is just equal to V1 final sine theta. So now I will substitute my values. We have M1 is 0.170 multiplied by the initial velocity of mass 1 and the y-axis. Now if you notice, mass 1, this is our puck 1, it's actually just moving horizontally. So meaning to say, if it's moving horizontally, it does not have a y component in its initial velocity. So so therefore our V1 final, or rather V1 initial on the y-axis is gonna be equal to 0. Again, let me just write this down. Why is it 0? Because the object is moving horizontally. It does not have a y component in its original velocity. Moving on, plus M2 0.170 times the initial component of its velocity, y times the vertical component, or the y component of its initial velocity. But then again, V2 is actually at rest, so I'm going to put a 0 there. Then I have M1 0.170 multiplied by V1 final y, which is equal to, once again, equal to V1 final sine theta. So V1 final is given to be 0.750. Sine theta would be sine of 30 degrees. Plus our M2, which is 0.170 multiplied by the vertical velocity, the vertical component of the final velocity of the second object, V2Fy. So now we have set up our equation. You just have to solve for the unknown, and in this case our unknown is just gonna be equal to the V2Y final, so we could set this as our x in your calculators. And plugging those values, you should be able to obtain that your V2Fy is equal to negative 0.375 meters per second. So now we have our v2fx, and we also have our v2fy, the final component of the components of the final velocity of the second object. So to solve for the final velocity of the second object, we just have to use the magnitude formula of a vector. So if we have the x and y component of the vector, so in this case we have vx squared plus vy squared, and we take the square root of that, would actually give us the magnitude of the vector quantity. In this case, our vector quantity is velocity, and in fact the question is only asking for speed, which in fact is the magnitude of velocity. Alright, so we use this formula to solve for the final velocity of the second puck. So we have v2 final is just equal to the square of the x and y components of the final velocity of the second puck. So we have v2 final x squared plus v2 final y squared. Substituting the values, we have the square root of 0.85 square plus negative 0.375 square. And this should give us that the final velocity of the second puck is equal to 0.929 meters per second, or approximately equal to 0.93 meters per second. And that completes the solution to the problem. We have solved for the speed of the second puck after the collision.